Hello, class. Um, Let me make use of this opportunity to welcome members of computer assisted applications to class today. Today, I am going to discuss homogeneous transformation matrix with the class. In this class today, we are going to employ MATLAB to generate object, just like this triangle that you are seeing here today using coordinate geometry. The generated object will now be moved in MATLAB environment by making use of homogeneous transformation matrix. What am I trying to say? What I'm trying to say is that MATLAB is going to assist us to generate objects of this nature. After we might have generated objects of this nature, in MATLAB environment, we are going to make use of homogeneous transformation matrix to move it to another location. Also, in MATLAB environment, we are going to view the object that we have generated in its original position, and at the same time we are going to view the same object in another position that it has moved to. What am I saying? At the end of this particular lecture, my students will be able to make use of homogeneous transformation matrix to move a generated object in MATLAB environment to another location that we are going to call translated location. That is what we are going to do in this class today. Now, based on what I've stated, it is now evident that the goal of this particular lecture is to make use of MATLAB to generate an object, and after we might have done that, we are going to employ homogeneous transformation matrix to move generated object to another location by making use of what we call homogeneous transformation matrix. To achieve our goal, it can be stated that our objectives are: 1. Generation of object in MATLAB environment. 2. Translation of the object that has been generated to another location using homogeneous transformation matrix. 3. To fill the object that has been generated in its original position and at where it has been translated to. 3 objects, and we are going to achieve those objectives now. We are going to achieve those 3 objectives now. To achieve the objectives, we are going to follow this agenda. I'm going to tell the class what homogeneous transformation matrix is. I will also tell the class the areas of applications of homogeneous transformation matrix. That will be our phase 1 of this lecture. Phase 2 of this lecture, I'm going to present to the class the homogeneous transformation matrix structure. In this area, I will present two-dimensional transformation matrix, and I will tell the class the key areas of 2D transformation matrix. For the sake of completeness, I will also discuss 3D transformation matrix, and I will also touch the key areas of 3D transformation matrix. Then, based on the 2D and 3D, I will try to discuss briefly ND transformation matrix, where N happens to be the number of transformation you are interested to deal with. N is going to be a value. N can be 2, N can be 3. If N is 2, that is 2-dimensional transformation matrix. If N is 3, that is 3-dimensional plane transformation matrix. N is 5, that is 5-dimensional transformation matrix. By the time we know 2D transformation matrix, we know the components of or what 2D transformation matrix contains, and we know what 3D transformation matrix contains, we can say something about ND transformation matrix. That's what we are going to do in phase 2. In our phase 3, for us to be able to know that MATLAB can help us better, then we are going to treat 5 examples. We are going to start with a point. A point is an object, and combination of points using coordinate geometry will give us a solid object. We will start with a point without visualizing it. We will now move to another area, which is going to be an extension of the first example, we show the original plot and we show translated point. Then after that one, we are now going to take three-dimensional points. We will use the information to come up with a three-dimensional chip, and I'm going to tell you there that if you have representation of the shape, the three-dimensional shape, you have the three rows that represents the shape. You can come up with the shape. That is, we are generating three-dimensional shape. And in this class, I'm going to use a cube. So for demonstration, we are going to plot the original cube, and we are going to translate the original cube to another position entirely using homogeneous transformation matrix. I've told you our objectives. The first objective is to create the object. The second objective is to make use of homogeneous transformation matrix to move the object that we might have that we have created to another position entirely. Then the third objective is just to fill the object that we have created in the original position and in the translated position. What we are going to do to 3D, we are going to do it to 2D. But one example of a 2D shape is a triangle. We will generate a triangle, and we are going to plot, and we are going to fill the original plot of the triangle, and we are going to see the translated triangle in its translated position. And the fourth phase is going to be demonstration of all these examples, all the MATLAB scripts that we are going to generate that we are going to develop under phase 3 will now be simulated in MATLAB environment, and thereafter we will conclude this lecture. Introduction. What is a homogeneous transformation matrix? Homogeneous transformation matrix is a matrix that contains n by n matrix, n by 1 matrix, and a 1 by n matrix. Three matrices in one matrix. Three matrices in one matrix give us homogeneous transformation matrix. Better still, we can say that homogeneous transformation matrix is a matrix that contains one n by n matrix, two columnar vector, three row vector. But in this discussion, we are going to consider 2D and 3D transformation matrix. Why? The reason is that the two transformation matrices, 2D and 3D, are used in robotics, in computer graphics, and computer vision. And that meaning that we used homogeneous transformation matrix in the following areas: robotics, computer graphics, computer vision, and geometric computing. Now, in robotics, the transformation matrix is used in coordinating frame transformation in manipulator kinematics. What am I saying here? When we talk about kinematics of the manipulator, homogeneous transformation matrix is used in manipulator kinematics to be able to find the poles of end effector of the manipulator, to find the poles of end effector of the manipulator, to find the, I've told you, we use HTM, homogeneous transformation matrix, for transformation of the frame in manipulator kinematics. That is, what we use it for there is just to find the poles of end effector. What is the poles? The poles is the position, linear position of end effector and the orientation when we know the angular displacement at the joint of the end of the manipulator under consideration. That is, if we know the angular displacement at the joints, that is, if you have many joints, we are going to have many angular displacements. And this information about this angular displacement, which we can say theta 1, theta 2, when we know how the joints are being displayed, we can use the information to determine linear position and orientation of the end effectors. Now, the same thing, when we know the linear pose of end effector of manipulator or manipulators, we can use inverse kinematics to determine displacement at joints. We achieve forward kinematics. Forward kinematics is about determination of pose when angular position at joints are known. Whereas inverse kinematics happens to be when we know the pose of end effector of manipulator, we can use the information to determine angular displacement at joints. Apart from usage of HTM in robotics, we use it in computer graphics, and that is what we are going to do here. We are going to create a graphic, an object, as a scene, and you are going to see how we are going to move the object from its initial position to another position entirely. That is what we use HTM for in computer graphics, because what we are doing, as I've told you, one of our objectives here is to generate an object using coordinate geometries And after you might have generated that, we want object to move from one point to another. We are now going to employ homogeneous transformation matrix to move it using the components of HTM that we are going to discuss very soon. We use it in computer vision for image registration and geometric correction. If you generate a given image, you have captured a scene and you import it to um, the MATLAB environment or any application for that matter or any package. You can register it after getting to the environment and try to do necessary corrections via computer vision. Apart from that, we use it in geometric computing. And what do we use it for there? We used it, in shaping, manipulation of a given shape. You manipulate whether you are interested in increasing or decreasing or deforming a shape. And after you might have done that, you now place it by properly align it. And that is usage of homogeneous transformation matrix. Four areas that are being used, and many areas are mentioned in this lecture. Now, let us now look at structure of homogeneous transformation matrix. And I've told you we are going to consider 2D homogeneous transformation matrix and 3D homogeneous transformation matrix, because those two transformation matrix or matrices are the commonly used in four areas that we have been able to mention. 2D transformation matrix, as I've told you in my introduction, a given homogeneous transformation matrix contains n by n matrix, which is stated here in the top left of this matrix. And I try to surround it with a rectangular box having red line where you are seeing my cursor. And this matrix is referred to as identity matrix. And why do we use it? We use it to preserve orientation of the object or the image that we might have created. And this is what they call identity matrix. This is n by n matrix. As you can see, 2D, two-dimensional plane is 2 by 2. Is 2 by 2 matrix. As you can see, this is 2 by 2 matrix. And this is what we are talking about. Then we are having what we call columnar vector. This is a vector. It is in this area. It is 2 by 1 matrix, second matrix. And this is what we call translation vector. Translation vector. And that is n by 1 matrix that we have, which is the same thing as columnar vector, is the same thing as a translation vector. So second vector, first vector, which is second matrix. It is a matrix, but we call it a vector because it has one dimension, one column. And this is another vector, which is a 1 by n matrix. 1 by n matrix. And for 2D, we are using 0, 0, 1. That is, the first element is 0, the second element is 0, and the last element in this particular row is 1. And this is what we call scaling vector, because this one indicates the scale of object in question. And we use this particular vector, row vector, to ensure that the projective space is consistent. What are we trying to say? By the time you make use of translational vector and n by identity matrix here, you are going to have a 2 by 3 matrix. And for us to be able to carry out multiplication with our object, the object is going to be 3 by 1 vector. And what I'm trying to say is that we need a square matrix here. To have a square matrix, this is going to be 3 by 3. Then we introduce this scaling vector. That is 2D will give us 3 by 3 matrix, which contains 1 n by n matrix, n by 1, or because we can extend it to this n by 1 matrix, because 2. Then we are now having 1 by n matrix, or 1 by n plus 1 matrix. Then we are now having n by n is original matrix. We are now adding a vector to it, a columnar vector to it. Then we are now having three columns, and we are having one row to these two. N by n. We are now having 3 rows, 3 columns. That is, 2D transformation matrix is a matrix that has 3 dimensions. It's of a matrix, or it is 3 by 3 matrix. Therefore, we can say for 3D transformation matrix, this is what we use to preserve the identity of 3D plane. That is 3 by 3 matrix, which this time around is our n by n matrix. We are now adding a translational vector. That is, this is the vector that is going to move our object from where it is now to another area entirely. And for us to be able to preserve the consistency of the space under consideration, we had a row vector, which I call scaling vector. And therefore, our 3D is 4 by 4 matrix, which contains 3 by 3 matrix, 3 by 1 vector, and 1 by 3 vector, or we say 3 by 3 matrix, 3 by 1 matrix, and thirdly, 1 by 3 matrix. And by the time we have this information, and we have the vector of the object that we are going to translate, and you carry out matrix multiplication, the number of elements in this row is now equal to the number of rows in the object, then we can find the new position of object under consideration, and that is what we are trying to say. But before I move to another slide, I need to tell you one thing, that here we are just generalizing it in robotics. When we know the angular displacement at the joint, instead of using identity matrix, we are going to make use of the information. We are going to make use of the information we know about about um, angular displacement that we know at the joint. That is this area, that is 2D 1, 1, that is this element will be cos theta, where theta represents the angular displacement at the joint where two links are where two links meet, and this element here, which is a T2D 1 2, will be sine theta, whereas T2D 2 1 will be minus sine theta, and this area is going to be cos theta. And I've told you theta happens to be the angular displacement at the joint, or angular rotation, the rotation at that particular joint. That is, instead of making use of identity matrix here, we are going to make use of what I've just told you. Having done that, we can now go to MATLAB examples without wasting time. We are going to start from point, and I've told you our MATLAB script should be able to contain three things. The first one is that we are generating a 2D point, and this is it. This is the 2D point that we are generating. That is, this is the coordinate geometry representing this point. That is, when you draw a line from where s is equal to 3, and a line from where y is equal to 4, they are going to intersect at a point P, which is denoted, or which can be denoted using P 3, 4. That is the point, and it is an object. A point is an object, and this is the original point that we have been created. And to translate this point to another area entirely, this is our translation, tx ty. That is, 3 is going to be moved 2 units away. That is, if 3 moves 2 units away, it's going to get to 5. And by the 4 moves minus 1 unit away, is going to get to 3. And for us now to be able to, that is, we have generated a point. That is the first objective, using these two statements. That is, load the information here to P location, and load the information here to T location. Now, we are now trying to invoke homogeneous transformation matrix, which is given to us here, because this is two-dimensional plane. And here, this is what we have here, you can represent like this. That is, this is a 2 by 2 matrix, 1 0 is 0 1, which happens to be identity matrix. And T1 T2 happens to be our columnar vector. T function of 1 is 2. That is the 2 in T location is T function of 1, and the T function of 2 here is minus 1. Minus 1 is going to be stored here. And then this is our row vector that we can call which we can call which we can call a row vector. And this is what I've presented to you. And now we are now having 3 by 3. And don't forget, the original point is given to you in as as 2 by 1 matrix, which is columnar vector, and must be 3, so as to be able to be able to, because these three elements you see this row, we multiply we multiply we multiply 3 by 1 vector. To make this one to become 3 by 1 vector, we are going to add 1 to this area. And to add 1 to that area, we have now been able to make use of this information. P here is a vector which is row 1. Row 1 is going to contain 3. Row 2 is going to contain 4. Then row 3 will now contain 1. Row 1 is going to house 3. Row 2 of P is going to house 4, and row 3 is not going to have 1. We have now converting 2 by 1 matrix using this command here, 3 by 1 matrix, so as to be able to have a vector that can be multiplied by transition matrix. They must have the same dimension. Let me just put it like that. You know what I'm talking about. After you might have gotten the same dimension with a transformation matrix, then we can now find the position of P, where it, the translated position. Then we are now going to take T here, we multiply it by P homogeneous, because by adding 1 there we have made it to be homogeneous. Then we are now at P translated. Now for us to be able to view the new position, then we use display command, DISP, and this is original. That is, by writing something of this nature, I've told the class this one is going to write the statement the way the thing is here. Say original point colon, then it's not going to use this command to display the content of this information here. It's going to display 3 and 3 4 as a columnar vector, but we want it to return it in row, just like what you see here. And that, therefore, we now transpose it. This is transposition. We transpose by making use of what we call superscript comma, superscript comma, or apostrophe. This is upper, by using this one, you are transposing this from vector to row, and that's why you have something of this nature here. The same thing here, the content of P underscore translated, that that happens to be the matrix multiplication of homogeneous transformation and homogeneous vector, then it's not going to be stored here. And for us to be able to display it, we now make use of, we want the thing to write translated point E is equal to what we are going to have here, and to write it in rows, not to present it in row vector and not columnar vector. Then we put apostrophe here. It's not style, and we are not making younger at all. We are just transposing it so as to be able to see what we are trying to say. And instead of writing this one, because this I've told you in one of our classes that when you make use of semicolon in MATLAB environment, you are trying to say that is the end of this row. Then this one is going to start from another row, and that's what I've just been able to do here. So having done that, then by the time we now run what you are seeing here in MATLAB environment, you are going to see what I'm presenting to you here. This is what you are going to see. By the time we get to the MATLAB environment, I'm going to demonstrate. That is, we have now been able to move the point that has a coordinate 3, 4 to point to another point entirely, which is 5, 3, by making use of this translation vector. Now, let us now see. Now, we have been able to see the point, but we want to see this point that we have been able to create, and this point that the point has been moved to, Now, to do that, this is what I've presented before now. What we are now trying to present here now is this. For you to be able to see this one in MATLAB environment, you are going to make use of the word plot. Plot. You are plotting a point, and the first point here, which is representing x coordinate, is a p function of 1, and y is p function of 2, and that one is going to give you the area where 4 and 3 intersect. We form this point, and for you to be able to show the point, we are now trying to say that you should use color blue. B stand for blue in MATLAB environment, and you should use O marker to indicate it. And this is going to be the marker size. The size of the marker that we are talking about here is going to be 10, and the thickness of the thickness of the line is going to be 2. That is that. Then, for you now to be able to retain this point that you have created, you said hold on. So don't want it to go off. Then you are now plotting the translated point. You are now plotting the translated point, and translated point is, we are dealing with what we call 2D translation matrix. Therefore, we are going to, when you want to plot, you are going to have x axis, s coordinate, and y coordinate. And for p underscore translated, this is the x, this is the y. Now, and the two meet at another point that we have moved this point to. And for us to be able to indicate the new position, which is a translated point, we use color red, and we mark the marker with x. We mark the marker here O. We use x here, and this is the size of the marker, and this, what I've used here, the thickness is of marker is 10, and the length of that x that you are drawing is 2. As you are increasing this one, you will see that your x is going to be increasing. Now, having done that, in order to represent, because this is a vector, in order to now try to show the direction of the movement of original point, then you are going to make use of vector field. To make use of vector field, you are going to make use of this command, quiver. And where are you moving the vector from, and at what distance? Under the mass are concerned, you are starting from this point where P1 and P2 intersects. Then you are moving them away from using T1 and T2, and you are making use of this color K, which is color black, and the thickness of that particular line is going to be 1.5. Then this is axis. You are selecting axis for your for where the thing is going to be plotted. But if you don't try to do this, the MATLAB is going to use customized or appropriate axis for it, where you are going to get it well. And the same thing with all this color. You may not put any color. The system is going to know that you are translating, and it's going to use different color. And for you to be able to see the grid, so as to be able to measure to read the point of intersection, and to find out that the thing is doing the correct thing that you want, and for you now to be able to differentiate between original point and translated point, and to show the translation vector, you just try to say original. Then the system, the computer, the MATLAB is going to see that you are referring to this, and the second one you are referring to this plot, and the third legend is referring to quiver, and the title of this work we use title. I've told you one time like that, and the title bracket open, inverted comma, 2D point transition. You can write anything you feel like and you close it and you terminate the statement using semicolon. By the time you now finish doing this, then you can now run your script that you have developed here, that you have been able to develop in this area, in MATLAB environment. And when you now try to click run, what you are going to get is this. This is I've told you color blue is going to be, and the size has been given. If you want it to be bigger than this, you increase the size. That is original position using color blue, and this is translated position using cross multiplication red, and the usage of quiver try to give us this direction, and the thickness is specified, and this is what we have been able to do. And we have been able to show that the point that we have been able to generate, which happens to be p bracket open 3,4, has now been moved to this particular position, which is position p prime 5,3, and the translation vector that we use try to give us this. By the time you change the translation vector, you want to make sure that this object is now moved to this area. You just try to work on translation vector and you are going to get it here. If you want it to go after this one, you do the same. And but you have chosen the axis. If you have not chosen the axis, the MATLAB is going to expand this axis so that it's going to take care of that particular area. And if you want it to move to this direction, you just specify the area. Let us believe that you are interested in this area, and this area is 2. That is, area is going to be 1. Yes, it's p prime 1, 2. That is the position. Then what you are now going to do is that you take 1 from 3, and that one is going to give you tx, because tx is now going to be 1 minus 3. That is, tx is going to be minus 2. And since y is 2, you are going to take 2 from 4, and 2 minus 4 is going to give you minus 4. For this thing to be located here, your tx is going to be minus 2, as I've stated, and your y-axis is going to be minus 2. And at the end of the day, this is going to be the location. That is, we are now trying to do our object as if the thing is moving in real time. And what has helped us to do that happens to be homogeneous transformation matrix. For the cube, that is another object, but the cube is a 3-dimensional object, and we are now trying to look at a 3-dimensional object translation, and this is representation of our cube. The cube has 8 vertices, and under normal circumstances, for you to be able to represent any 3D object, you are going to make use of the 3 rows. This is the first row. The entire row, you need to define it as a point. This is another point. This is a second row and third row. And you first of all draw your object and take good care of the vertices. Then you now present the vertices, and this one is now going to be used to generate a cube. And we want to generate this cube, and after you might have generated it, we want to move it the x points. That is, this under normal circumstances, in this area, what you are seeing, this column, this row is for the x, this row is for the y, y-axis, and this one is for the z axis. That is what I'm trying to say. The starting point is 0, 0, 0. X is equal to 0, y is equal to 0, and what do I call it? Z is equal to 0. At this point, everything is 0. That is, let me just show you that here. This is the point. At this point, x is equal to 0, y is equal to 0, and z is equal to 0. That is that. That is, first of all, draw your object and you take all these vertices, and all of them are the one. That is, when you are here, you take care of x is 0, take care of y is 0, take care of z is 0. You have completed this particular area. And when you come to this area, you can see that z is 1. The last coefficient is 1. But when you look at this area too, at this point again, y is 1 and x is 1. Therefore, this one is 0, 0, 1, 0, 0, 1, 0, 0, 1. So that is what we are talking about. And when you get to this particular side, when you get to this area, for instance, z is 1 here, y is 1 there, x is 1. This one is going to give you 1, 1, 1. And that is how you are going to read it. After you might have read the information, that you have been able to analyze in your work, you now come to this particular environment, you write it the way, like the dot. We at a dot axis, we have 0, 0, 0. And then at this particular area now, here, I told you that the coordinate there is going to be 1, 1, 1. So you write them like that. So it doesn't matter that the thing must follow the way it is here. It doesn't matter, but you arrange it, the system will know how to position it, and it's going to generate the key for you. And when the key is now generated, you have generated a key. Then we want to move the key away from this point to another point using particular translation that we have here. So this is translation. Then we have generated, and from here to here, this is homogeneous transformation matrix here. That we have defined our columnar vector, which is transition vector. We have gotten that. We have gotten 1, 2, 3. That is what we got to move it away from. Then for us to be able to develop what we call identity matrix, then with usage of I is going to generate identity matrix that's going to be 4 by 4. That is, we are going to have 1, 0, 0, 0. Row 1, row 2 is going to be 0, 1, 0, 0. Row 3 is going to be 0, 0, 1, 0. Row 4 is going to be 0, 0, 0, 1. That is what are we trying to do. We want to have a diagonal element to be 1, and other area of the diagonal, there will be zeros. So that is what I is generating. And don't forget, the column 4, of our transformation matrix supposed to contain the translation matrix, which is this one. Then under normal circumstances, you now try to tell the system that column 4, what is going to occupy column 4 is going to be 1, 2, 3. And therefore, you are now reserving n by n matrix by trying to say that the whole of that n by the 3 by 3 matrix first is going to be reserved the way they are. That is identity matrix that you have created. They are going to remain the way they are, and therefore, but don't forget, column 4 supposed to contain 1, and column the row 4 supposed to contain the end of 4 by 4 element supposed to be 1. Therefore, to do that, you now try to tell the cube here happens to be what we call this is 3 by 8. To make this cube, this particular cube to be translated to make it a 4 by 8 matrix, so that we can try to carry out matrix multiplication using transformation homogeneous transformation matrix, which happens to be 4 by 4, and this one is going to be 4 by 8, so that multiplication is going to be possible. Then we are now trying to make use of ones. It's not going to write ones here, in this row. That is, they are going to create row 4. Row 4 is being created by these ones, and just try to take care of that. We have now gotten homogeneous cube, and when we now get homogeneous cube, which happens to be 4 by 8 matrix, and we got in translation homogeneous translation matrix, which happens to be 4 by 4, we can now try to translate this cube to another position given by us by this, by making use of this information. And after we might have done that, we can now view the figure, at original position and at translated position. But one thing here is that, as I've told you before now, we want our figure to be on one window, on one figure. All our plots, rather, to be on one figure, which is one window. We are now making use of subplot. Here we are making use of one row, two columns. That is 2 rows, 1 row, 2 columns. Column in the first plot of this figure. Then original plot is going to be there. But here you need to take note of tree. Tree is trying to tell you that you are dealing with three-dimensional plane, 3D. And 3D, for the representation of 3D, you need X, Y, Z. And this is the entire row here represent the key function of 1, comma, dot, dot, meaning that I want the entire row to be plotted. Then this one you are having here, I want entire row 2 to be plotted. I want entire row 3 to be plotted using blue color, and you mark that area with O. I'm using blue. And under normal circumstances, the title of this plot is original cube. And we use this time around, this is another way of doing axis equal. It's going to look at the appropriate axis to be able to put your plot there. And grid is going to be on, and you need to tell the plot that I'm dealing with a 3-dimensional. Please don't give me 2D. So fill 3D. Then for the translated cube, you are making use of this. You are placing it in a second, because we are having 1 row, 2 columns, second plot, and that's where the cube that has been translated is going to be. And to represent 3-dimensional plot, you are going to specify the all position of x. The x is occupying the position that all the element of y is occupying. That is what you are going to generate here: the first row, the second row, and this is third row. And you are making use of a red color, and you are making use of a 0 marker. And for you to be able to see the title, put this, and the axis equal, grid on, and you can fill 3-dimensional plot. By the time you finish doing this one and you go to the run, then this is what you are going to see. So this is original plot using blue color to draw the vertices, and this is the translated cube using red to do that. And what are we trying to say? Let us look at x. When x is equal to 1 here, we try to say that x must move 1 unit away, and that's why we are saying 2. And here we are trying to say that the z must move 3 units away, and that's why we are saying 4. That's why we are saying 4. And this is why. And you are trying to say that your y is supposed to be moving 2 units away, and that's why we are saying 2. And the same thing here, we are having what we are having, and that is why we have been able to get everything done. So, and that is representation of that. And for the 2D, because we need to show 2D, and we are going to tell you that with just 2 points, you can draw 2-dimensional plot, no matter how the shape will be. But don't forget, you need to first of all carry out the analysis and capture the coordinate. Now, for the 3D, we are having something of this is a row 1, this is row 2, that form the two rows form the triangle under consideration, which is a 2 by 3 matrix. And you know that for 2D transformation matrix, you are for you to be able to convert 2D object to homogeneous transformation matrix, you need 3 by 3. Therefore, there is need for you, instead of having 2 by 3 here, you need to carry out to make this one homogeneous by adding another row. But this is the real object that is showing that is here. This is a good representation. This is row 1, this is row 2. That is at beginning. When x is equal to 1, y is going to be 1. That is the first point. You mark it, and that's why we did point first. And at this particular area, when x is equal to 1, let's say this is 0, this is 1, y is equal to 0, the same thing here. Then at x is equal to 5, which is the middle, this is 0.5, x is equal to 5, and y is going to be 1. And you can see, that is, we can now plot something of this nature. That is triangle. And we have generated triangular shape. And we are moving that particular triangular shape to 0.5 away from where every x, all this x is 0, 1, 0.5 is going to be moved 0.5 away. That is, 0 will be moved to 0.5, 1 will be moved to 1.5, 0.5 will be moved to a point which is 0.5 plus 0.5, which is going to be 1. And that is what, and the y2 is going to be moved 0.5 away, and these are our y's. So y is going to be in new position 0.5, 0.5, and 1.5 in new position. So having done that, to create transformation matrix, which must be able to contain 3 different matrices. That is, the first one happens to be n by n matrix, which is going to be 3 by 3 matrix, and which is going to be 2 by 2 matrix, since we are dealing with a 2-dimensional plane, and that is why we are now creating high function of 2. That is, this one is going to create a 2 by 2 identity matrix. Then to add a vector so as to be able to have 3 columns, we are now having a transitional vector, which is a columnar vector here, this one. And to have a 3rd row, so as to be able to have 3 rows, 3 columns, we are now adding this row vector to it, which we call scaling factor. It's a scaling vector, and we are now having 3. This is a transformation matrix, homogeneous transformation matrix. It contains many matrices, and that is why we have gotten this. Then for us to be able to get 3 by 3, so that multiplication with homogeneous transformation matrix is going to be possible, we try to take this shape and we had ones on the bottom, and we can now carry out our multiplication. This one is 3 by 3, and this one is 3 by, this one is because by the time you had 1 here, this one is going to be 3 by 3. Therefore, we can multiply the row vector to the column vector here, so as to be able to get the result that we are looking for. And this one is going to give us where the thing has transited to. The result is going to be loaded here, and this is our plot. We want to see, and I've told you need just two points, x and y. All the elements in the first row, which happens to be x, all the elements in the second row, which happens to be y, they are now going to be used to plot, to show the shape that we are talking about here. And we are making use of blue color again, and we are making use of a solid line, thick line for that, and the length of that line is going to be 2. We hold on our triangle here, and our triangular shape here, but the triangle that we already generated, we have moved the image of it to another area entirely. We call it a triangle translated position, and I've told you to represent to fill this particular figure, under normal circumstance, you need x comma y, and the whole of element of x in row 1, that of y in row 2 will now be written here, and we are now making use of red color using a dash line, and the line thickness is going to be this. But if you don't put this, I'm trying to tell you that the computer package is going to put appropriate line that is going to use to differentiate it from this. And for you now to be able to fill the line with color, then we use the command fill. That is, you are filling the triangle with color blue at the face, and the thickness of what you have used is 0.2, and you are filling the translated triangle. The word fill, if I want you to fill, you use fill, and you indicate the triangle that you want to fill, and here we are filling it red at the face, and the thickness is going to be 0.2. And for you now to be able to write the legend, so that this one is original triangle and this one is translated triangle, and the title is a 2D transitional 2D triangular translation. And by the time you now run this thing in MATLAB environment, this is what you are going to see. This is original triangle. As I've told you, this is the only point that you need to indicate. The system will know that since you are dealing with that, it's going to draw this one for you. The same thing here, you use dash line to draw this, and you can now agree with me that at this point, s is 0 and y is 0. Therefore, at this point, you can see that x is 0.5 and y is 0.5. It has moved from 0 to 0.5. The distance between the original point and the translated point happens to be 0.5, as you can see. And here is 1. You can see that here is 1.5. That is, at this point, where we have 0.5, comma 1, is now going to be 1, because 0.5 has been added to 0.5 here to have 1, and the 0.5 has been added to 1 to have 1.5. That is, the coordinate point here can be named as 1, 1.5, and so on and so forth. And this is a translated triangle, and this is original triangle, and this is representation of 2D transformation object. We have done that. We have developed the script that can be run in an environment, and you are going to get the result. Now, for us to be able to do an application problem, say a scenario problem, I now try to bring this particular problem to you. And the problem states, the problem can, this is the problem, and I read, a robot needs to move from a position. This initial position. We are going to indicate this is point A, and point A from 2, from x-axis 2, from y-axis 3, and that is what we have. Then it's moving to this position B, which is 8 and 5 in 2D plane. And the idea now is that we should determine translation matrix required, and that is Tx, Ty. And for you to be able to determine Tx, Ty, that is, you say T is now going to be equals to B minus, after you might have declared A. That is, don't forget, all these objects, they are columnar vector. That is, our A will now be equal to, you open a bracket, 2 semicolon 3. That is, then B is equal to you open rectangular bracket, 8 semicolon 5, you close the bracket, and you terminate with semicolon. Terminate the first one with semicolon. Then for us to be able to determine translational vector, then you are going to say C will now be equals to B minus A, and that is just, you have calculated that one, and the content of C will now be equals to 8 minus 2, 6, 5 minus 3, 2, 6, 2. But you don't need to do anything. You have instructed C location to house the information that we have just calculated. But after moving, the robot detects an obstacle and adjusts its position by additional translation of 1 minus 2. That is, we are now having another translation vector. Another translation vector. Now, then you are going to define that particular translation vector, and that one is going to be, let's say, t t1 or t2x, comma t2y, and you send this information there as a rectangular bracket. You open that, 1 semicolon, minus 2, you close it with a rectangular bracket, and you terminate by semicolon. You have stated that. Now, what are we now going to do? They now try to update the script so that it can be used to find the final position and visualize the position. Two things. You are going to find the final position and you are going to see it. Now, what we are trying to say is that by the time the robot tries to move from this location to this location, the robot finds out that there is an obstacle along the way and now tries to navigate to another area entirely so as not to be able to hit the object. And the distance from where it takes another direction to the final point is given to us, which happens to be translated vector. And what we are now going to do is that you first of all find transformation matrix here. You find transformation matrix with a first position here. You now multiply the transformation. They are connected in series. They are cascaded, and as a result of that one, since they have the two are cascaded, you now multiply the transformation 1 and transformation 2 to be able to get total transformation. And then the final position, the final position where the robot is going to be now, is going to be total transformation times the initial position. So that is going to be the final position. But we are going to visualize the part. Therefore, we are going to employ quiver, the command that's going to show the vector feed. That is the information, and this is the manipulation for us. So we first of all determine initial translation, which is T1. No, this one is supposed to be small letter 1 and small letter T rather, and this one is going to give us 6,2, but you don't go into that. Secondary translation is given to us, and the total translation is now going to be the translation given to you by this and this one is going to give you this. And to convert the analysis to program, we are now here. So here we are having this. So we are having point A, the starting point, and we are having final point with the target position before the robot try to see what we call an obstacle. Then we have given translation vector C, the final one. Then we are now trying to find the T1 vector, translation vector. We can use lowercase for T. Then that one is going to be the difference between this and this. Then you now find, you now use this information to obtain transformation vector, homogeneous transformation vector 1. You use this one to determine transformation vector 2. This is now taking you, because this is translated vector and it's now here now. Then under one circumstance, translation homogeneous transformation vector is T for T1 is going to be, because it's 2D, 1 0 and 0 1 happens to be what we call identity matrix, and we are now realizing our information here and 3 by 3 matrix, and this third one happens to be what we call our scaling vector, so as to be able to make sure that our homogeneous transformation matrix is 3 by 3. And for the 2, we have this one too. And therefore, to be able to get to the final point that this translated translation vector is going to take us to, we need to determine the total is going to be the one to take us to that particular area. Let us believe that we still, the robot has not gotten to the position and try to see another object again. We can try to say that it should go to another area. provided we know the transited vector, we are going to still get to that point. So here, then we are going to find homogeneous transformation for the vector here, for the for the coming focus, so that it's going to give us the 3 by 1 matrix, which happens to be a columnar vector, so that it can be able to, we can use it to multiply 3 by 3 matrix. So that is what we have now been able to do here, so as to be able to get what we call 3 by 1 matrix, which is a columnar vector instead of what we have 2 by 1 matrix here, which is a columnar vector too. Then this one is going to give us the final point, and this particular one is going to give us the initial point. So we can now visualize, and then when you are now visualize, don't forget this is a line. You still need to use to visualize the first point here, then you need only 2 points. You need only 2 points, this and this, but you need quiver to be able to show the direction of that. And that is why, here for our plotting of the point, just the way we did before now, our point A is going to have x and y, and it's denoted using O to represent blue, and the marker size is going to be 12, and the line, the line of that particular marker is going to be 2. Then we hold on. We now try to represent the second point where the object is with the same thing that we have done, but now we are making use of color red, and we are making use of x to indicate that particular position, and the size of x is going to be this, and the line, the thickness of the line that form this x is going to be 2. Then for the final plot, where the thing is going to be, because we have 3 different points, A, B, and the transited A, and this is transited A, which is given to us like this. We are making use of a green color and using this sign, and the marker size is this, and what have you. Then for us to be able to indicate the line that connects point A to point B, and the point B to final point, then we use the line that connects A1 to the transited vector is represented by this using quiver, then vector feed, and we are making use of block, what do we call it, a color represented by K. That is, if you want to know the color, you need to know the code. But K is black. Then the color for M, and from B1 using this translator, and we now get to this area. And this one is now going to show how the things are linked, because we have the transition vector for this. We have transition vector for which happens to be transition vector obtained by taking point B from point B. Having done that, we can now view this is the limit of our x. You can put it, you may not put it, doesn't matter. What you just need to do is just to write, this one to write at point A1, and what have you here, A2 minus 0.5. You wanted to indicate this line, that is at that point 2,3. This is a text. To write text on a given point, at that particular point, this is the what is given to us as the coordinate geometry of that point, and coordinate geometry of B is this. And at that point, you are going to write text, and you indicate where the 2 happens to be. That is, B1 is x, B2 is y, and not to be able to write it so as to be able to for that particular area, for you not to have write this one on this one, so that the thing is not going to be readable. Then we now add the +4, so that it's going to move away from where we move away from B2, which happens to be y. So to move it away, and to move this one down, so that it's not going to be where A1 and A2 are. So then we now try to but to write the text there, you write text, and for you now to be able to write the information on what have you to, instead of using legend, or we try to use this, and you can still use this particular information to be, and you can make use of this print function. But I prefer display. I prefer display for my or instead of writing all this one, why can't you just write legend? Because legend is going to know that this one will belong to this one will belong to this one is going to belong to this. That is, the first legend is going to be for the plot of A, which is original point. The second legend is going to be for the plot of B, and the final point is going to be for that. Then if you write a third legend, a fourth legend rather, is going to be for the feed that link A, point A, to the to the transited vector, and the fifth one is going to be this one. If you don't want to use this one, just write legend, and legend is going to do the job for you. Then this is what I'm trying to say here. You can see that under normal situation, this is our blue color that represent what have you. But by the time you write x, this is what x is going to give you triangle, and the other one is going to give you triangular. X is going to give you rectangular shape, and this one is going to give you what have you shape. And the text that we have written is now giving us this value, the value that we have written here, the value that we have written here, and the value in this area. And if you use legend is going to give you all this information. But here they have been able to tell us that we can still use what we call text. And the text that we are seeing here is, since we don't know the name of this information, we just try to use the content of this information that we are going to obtain from this particular area here, to be able to write what we are trying to say here. Because the final up here is going to contain two variables, two constants. That is one for x, one for y. The one that is occupying position 1 of final homogeneous, and the one that is occupying what we call, that is when we arrange it in rows, the one that is occupying row 1, the one that is occupying row 2. So that is what we now have here. But that is what we have here. And what we can do, as I've told you, is that you can still write this one, but after you might have write that, but just because we want to write text, on top and what have you, that is why we have been able to do this. So having done that, that is the end of this lecture presentation. I will now take the class to the MATLAB environment, where we are going to demonstrate, or where we are going to run all the programs that we have been able to present in this lecture. But before I do that, let me just give the summary or the conclusion of what I've done so far. That is, here I've been able to tell the class what homogeneous transformation matrix stands for. And I told you that it's just a matrix that contains three different matrices. That is n by n minus 1, n by n matrix, n by 1 matrix, and 1 by n matrix. Or better still, we can try to say that it is a matrix that contains n by n matrix, a columnar vector, and a row vector. And you can go further. The columnar vector is translation vector, whereas the row vector is what we call scaling vector. And in two-dimensional matrix, we are now having 3 by 3 homogeneous transformation matrix. In 2D homogeneous matrix, or in 2D in a 3D plane geometry, our homogeneous matrix is going to be 4 by 4. We are going to have 3 by 3 as an additive matrix. We are going to have a transition vector, which is going to be a columnar vector, and we are going to have a row vector, which is going to be a scaling factor vector. Then, I've told you that, and I told you the 4 areas of application of homogeneous transformation matrix. I told you that the thing is being used in robotics for forward kinematics and inverse kinematics. And I told you what I mean by that. Then we use it in computer graphics, which is what we are doing. We are drawing using